Can you see the screen?
Everything's good.
All right.
So you might have to just stop sharing your screen and click that little box in the bottom left hand corner of the dialog. Okay? So when you go to share your screen, before you hit the screen that you're going to share, in the bottom left hand corner there's a little clicker box, check box, share display sound. And try again, please.
The informal definition
That's
of
better.
There you go. You can hear it.
defined
Oh,
as
that's an
a
instant-
form of rotating a shape,
Put it up a little bit.
rectangle or
Yeah,
circle
turn it up a
on
little
an
if you can.
axis, resulting in a geometric shape akin to a donut. This donut-like shape is what we know as a torus. In this presentation, we will be investigating the volume for
Ooh.
torus through three methods: triple integration,
No, that's
the
all right,
Washer
let it run.
method,
That's
and
fine.
the Shell method.
Is it still really
In
quiet?
addition, we will also be
It
discussing
is, but it
about the
needs to run.
applications of
I can hear it
torus.
okay.
Yeah.
Hold up.
Just
What is a
just
torus?
let it run.
Messi.
A torus is the rotation of a set of two-dimensional bipolar coordinates about the z-axis. The rotation around the axis is what separates the two focal points of the bipolar coordinates, resulting in the donut shape. The parameter of the torus,
I mean, the volume's a bit quiet on my end, but I can hear it.
capital R,
Yeah, just
represents
leave
the
it. It's
radius
fine.
of the circle from the z-axis. This is known as the major radius, and its angle is represented by phi. Lowercase r represents the radius of the circle going around the z-axis. This is known as the minor radius, and its angle is represented by theta. In the three-dimensional plane, the torus is represented by toroidal coordinate system. The system of toroidal coordinates is labeled as curvilinear, which enables quantities to be depicted as trigonometric functions on a given radial surface.
In this section, we look into its application by investigating the torus of revolution and Horn torus. Looking into Andy Sloan's 2006 donut code of the torus that rotates about the x, y, and z axis, using ASCII characters to give the shape a clear visual of the spatial dimensions. Delving into the mechanics of how to render a 3D object onto the 2D screen requires an understanding of how to draw its donut shape. The torus is a solid of revolution, using the cross-section of the shape, namely the circle, to rotate around the axis of the torus. If the axis of the revolution doesn't come in contact with the circle, the surface creates a ring shape, which is coined by the term torus of revolution. Examples of this in the physical world are glass lenses that utilize spherical and cylindrical correction, called toric lens. Compared to the conventional contact lens, which have spherical surface, the toric lens are made from a sliced section of a torus. These lenses are fitted for those who suffer from astigmatism and are created with a specific optical power and focal length where the two orientations are perpendicular to one another. Derived from the axis of revolution, when the distance is decreased and is tangent to the circle, the ringed torus transforms into a horn torus. In physics, it is commonly used as a dynamic visual aid to convey scientific processes and laws on a profound level. Detailing complex concepts through these pictorials allow physicists to draw a common understanding between abstract mathematics and human comprehension. An example of this is seen in the image of the uncoiling horn torus, conveying a schematic of the photon-electron transition as a resonance.
The torus in toroidal coordinates are defined as this, where ρ is between 0, the minor radius, and the major radius, and theta and phi are between 0 and 2 pi as their angles. To derive the formula for the volume of a torus, we must first get the integrating factor and triple integrate it with the bounds being previously seen as the definition of the torus. We must find the integrating factor by finding the Jacobian of these following parameters for x, y, and z.
The second method is called the washer method, a method of calculating the volume of an object with a hole in the center. This method makes use of the cross-section of an object. In the case of a torus, the cross-sectional area at any given height is a washer or a disk. Given that the torus being used is in a flat orientation, we would be required to solve for the x variable in respect to y. This is because the integration in respect to the y-axis requires a function in terms of y. The first of three steps in calculating the volume of a torus is finding the equation for the inner and outer radius. In the case of a circle on the x-axis, it is possible to solve the equation for the variable x, which results in two possible equations. The first being x equals h minus square root of r squared minus y squared, and the second being x equals h plus square root of r squared minus y squared, with the first of which being the equation for the inner radius of the torus, and the latter being the equation for the outer radius of the torus. The second step is calculating the area of the washer using the inner and outer radius. This can be done through the subtraction of a circle with the inner radius from a larger circle with the outer radius. The final step is integrating the area of the washer, with the top and bottom of the circle being the bounds. In this case, the upper bound would be r and the lower bound would be minus r. By solving this integral, we can obtain the equation for the volume of a torus, which ends up being equal to 2 pi squared r squared h.
The shell method involves shells that are created by approximating a given object and rotating these shells around the y-axis, as shown in the photo here. These are called cylindrical shells, and the combination of all cylindrical shells gives us a torus. Since we know this, we can calculate the volume of a torus by combining the volume of all cylindrical shells. And the volume of the cylindrical shell can be found by calculating the difference between the inner and the outer cylinders. Since we have determined that the sum of all shells would result in a torus, the sum of all cylindrical shell volumes would be equal to the volume of a torus. Summing all the volumes would be the same as integrating the approximate equation of the volume of a cylindrical shell, due to the definition of an integral. Now that we have the formula to calculate the volume of a torus, we can define the boundaries and integrate the formula. Integrating via the substitution method results in the volume of a torus equaling to 2 pi r squared times capital R, where r is the radius of the circle and capital R is the distance from the y-axis to the center of the circle. Torus are complex objects that require deep understanding to define how to represent them as well as calculate the volume of a torus. There are three primary ways to find the volume of a torus: the shell method, the washer method, and using toroidal coordinates. The toroidal coordinates requires a strong understanding of integration, whilst the other two methods rely on a fundamental understanding of calculus. As a whole, the different methods of calculating the volume of a torus may be applied to real life scenarios, such as creating visual models, both digitally and physically, which may in turn be used as teaching aids, practical demonstrations, and commercial reproduction of the shape.
Okay, thank you very much. Well done. Look, I don't mean to be rude. I'm not going to call for comment. I'm just going